السلام عليكم. السلام عليكم. السلام عليكم. Okay, any question before I start? Okay, so before we start, I mean, if anybody has a question, we can take the question. Otherwise, we'll move into the lecture. I'll not be able to answer the chat questions live. I mean, we can answer them at the end of the class because it's difficult for me to read the chat and give the lecture at the same time. So I'll just read them at the end. But if you have any question, you can raise your hand or you can speak at any time stop me during the class. Okay, but the chat will be difficult for me to read. But I mean, you can ask verbally any question you like at any time. Okay, so in order to revise last class lecture, it would be good if we can take an example to refresh what we did last time. So this example says, calculate the small signal voltage gain of a common source amplifier that we are seeing down here. And we have ID equal to 1 milliamp, sorry. We have a mu and COX 100 microampere per volt square. We have a threshold voltage of 0.5. And we are given here specifically that lambda equals to 0. This means that we should ignore the R out, assuming that it's infinity. And then after that, we need to make sure that our transistor is in the saturation region. So the first thing is that we remember that the gain of a common source amplifier is equal to Gm times RD. Okay, so we know what is the value for RD here, and we need to find Gm. If you remember Gm from last class, it was given by this relation, square root of 2 mu n COX W over L, and it's multiplied by ID. All of this is. You don't have to memorize this relation of Gm. That will be like it's a given thing for you. So now we know mu n COX multiplication. We know W over L here, and we know ID is 1 milliamp. So it's just direct plugging in the value. So it's equal to square root of 2 multiplied by 100 times 10 to the power minus 6 because it's micro. And then W over L is 10 over 0.18. And this multiplied with ID 1 times 10 to the power minus 6. And therefore, our Gm, if you calculate this, it will come out to be 1 over 300. And this is the book answer. This example is from the book, so I don't have to waste time doing the calculation. And the unit for the Gm is ohm inverse, because it's like, if you remember, di over dVGS, therefore it's a 1 over ohm. Okay, so now I can plug in the gain again. It's minus Gm multiplied with RD, and therefore it's 1 over 300 multiplied with 1 kilo ohm. You can see this is ohm inverse unit and this is ohm. They will cancel each other because the gain, it's voltage over voltage, so it does not have a unit. And this becomes a minus 3.33. So this is the gain of this circuit, a common source circuit. Now, just like if we remember the voltage headroom problem, if I want to increase the gain, one solution is that I increase RD. But if we increase RD, we might leave the saturation region. So we have to be careful about this. Now, how can I calculate the VGS? Calculation. So VGS is basically equals to V threshold plus square root of 2 ID over mu n COX W over alpha. More I brought this ratio. If you remember that the ID equation, ID in the saturation equal half mu n COX W over L VGS minus V threshold square. Now the lambda part is lambda 0, so we are ignoring that part. Now, if I want to put VGS on one side alone, so I have to take the square root of both sides and then make transfer the V threshold to the other side, then I will be having this equation that is given here. So V threshold is 0.5 plus square root of 1 milliamp 10 to the power minus 3 divided by 100 times 10 to the power minus 6. This is the mu1 COX value multiplied by W over L, which is 10 over 0.18. And then I get VGS equals to 1.1 volt. Now I want to make sure is the transistor remains in the saturation region or not. You know that our condition we should have first we need to find also VDS. So VDS is equal to the VDD minus this voltage drop that across this resistor. So it will be VDD minus ID times RD, and we know RD, we know ID, and we know VDD. So all of this will give me that VDS equal to 8 volt. So now I need to make sure that VDS, this should be greater, is it, I mean a question mark, greater than VGS, which is 1.1 minus V threshold 0.5. So 1.1 minus 0.5 is equal to how much? It is 0.6. So is 0.8 greater than 0.6? Yes, it is indeed. Then this means that the transistor is in the saturation region. Any question on this? So therefore, we're done from this example. If there is any question, I can answer it on this example. Okay. If it's fine, then we can move forward. So this is just, again, a summary from the book for the solution, if my handwriting is not clear. Now you remember the voltage headroom problem. We said that the gain depends on the load resistor, which is RD. So in order to increase my gain, I need to have a larger RD. But what's the risk in doing so? I might be leaving the saturation region. Why? Because we said that the VDS is going to be affected by the voltage drop across this resistor RD. So if I have a larger RD, this means I have a larger voltage drop across it, and I might be more prone to leave the saturation region if I have a larger RD. So what is the solution? How can we solve this trade-off? We can basically replace the RD, this RD, we can replace it by a transistor that acts as a current source. What does this mean? If I replace this RD, with a transistor, like this one that is given here, so just from point Y here, this is a point Y. So the upper part will be same as what we have here. What's the advantage of doing so? One thing is that I will be able to have a larger resistor without putting a physical RD. Like this transistor will give me a large output impedance, and it does not take larger voltage drop across it again. So this, if I look from here up on this transistor, I will have an impedance that's given by R out or R0. So this R0 or R out is typically a large impedance value. If you remember, it's 1 over lambda times ID. Okay, and usually this is a large value in a few hundred kiloamps to a few, few hundred kilo ohms to few mega ohms. It depends on the transistor and the currents that we are having. Okay, so this gives me a larger impedance, but it does not take a larger voltage drop. Means the voltage drop across it is a VDS here. It's not related to this value of this R out. So it's not depend. I mean, if I place a physical RD as this one here, the voltage drop across it is RD times RD. But here it's a VDS. It does not depend on this impedance of the transistor. Therefore, I can gain two things. I will have a larger impedance related to the gain, and I will not have a larger voltage drop across it, so I will not be very prone to leave the saturation region. Therefore, this is an advantage for me. So I can replace the RD with a transistor that acts as a current source. Okay, is this part clear? Now, if basically you need to make sure that you connect the transistor from the drain side of it, from the drain side. This is the source side. If we are looking from the drain side, then we will see this R out. But if you by mistake connect it from the source side, as you can see here, you will not, so looking up here and looking down here, we will not see this large impedance. Opposite, we will see a small impedance that's given by the value of 1 over GM. So here we will not have a good impedance, and therefore it's not a good way of connecting my current or my transistor load, which we can call it as an active load. So it's not a good way to connect. And you can prove from the small signal model for this transistor that you get an impedance given by 1 over GM. Okay. Now, what we want to say, we can, if you are interested, we can also later prove on this part that we are giving down. If we look from the source side, we can see 1 over GM impedance. Okay. Now I just want you to know these things. So if I look now, forget about the last column. We just want to guess them ourselves. So if I look on this transistor, so we have the gate of the transistor in order to act as a current source should be fixed to a DC voltage. So this is the gate is fixed to a DC voltage, and we are looking from the drain side. So those two conditions make it that it's act as a current source. And therefore, my out impedance that I am seeing down from node X is given by R out. And that's what's here. So this is a good load in order to get a high impedance. Similarly, this is a PMOS. So the gate is connected to a DC voltage, and we are looking from the drain side up here. Therefore, we will see also an impedance of R out. Now, this part, this one here, we call it the diode connected. If I am looking from the source side, again, I will see 1 over Gm. If lambda is not 0, then we will see that it's in parallel with the R out. If you even just put it 1 over GM, it's also correct. Because 1 over GM is very small compared to the R out. So if they are in parallel with each other, almost it will be equal to the 1 over GM. Similarly here, it's also we are looking from the source side, so we will see 1 over GM. And again here, it's diode connected when the gate and the source, sorry, when the gate and drain, they are shorted with each other, and we are looking down here on them, then we will also see 1 over GM. Similarly, this is a diode connected, but it's a PMOS. So the gate and the drain, they are shorted with each other. So once you will look up on them, you will also see 1 over GM. In a nutshell, if you are looking from the drain side, you will see an R out. If you are looking from the source side, or it's a diode connected device, you will have a 1 over GM. Diode connected means that the gate and the drain, they are shorted with each other. Okay, so I want you to know this for a fact, that if you are again looking from the drain side, you will get an R out unless it's a diode connected. The gate and the drain, they are shorted with each other, then you will just see 1 over GM. Also, if you are looking from the source side, you will see 1 over GM. You will see a small impedance. We need to keep this in our mind in order to make the things easier for us. Okay, so now I have a common source stage with current source load, or with an active load. And I want to find the gain of this stage. Somebody was raising hand. Ibrahim?
Yes, ma'am.
Yes.
In the previous slide, you mentioned that by adding a transistor, we not only make the RD independent of the R out, we also we don't need to. We also get a very high impedance. So what's the downside of using a transistor?
Mostly, it isn't not much downsides. It's a good thing that we want to do. So basically, we, as you mentioned, we get an output impedance that is high, and it's not related. The voltage drop across it is not related to the value of the impedance, so they are not proportional to each other. So I'm not at the risk of leaving the saturation region, and also I don't get much of chip area. Typically, if you want to create a large impedance, you need to have a larger area in your chip, and that's by cost money when you buy the area by money in the chip. So that is something bad, that you use an area, large area, just for creating an impedance. So that's also a disadvantage that comes with using a real resistor. So typically in most of the circuits, they try to have transistors to replace the resistors. So it's a good thing.
Okay, thank you.
Okay. Yes. So now let's try to find how much we will get gain from having a current source as a load. Now we can replace it with a small transistor, small signal model of the circuit. So basically this part down here, you remember it. So this is the drain. There is an R out, and it's in parallel with GM1 times V1. And this is the source connected to ground. And we have here Vn. And this is our gate. And this is our source. And then here we have V1. And from my drain of the transistor 1, I will be connected to an R out 2 in parallel with GM2 times V2, and those, they are connected to ground. Why ground? The source of M2 is basically connected to VDD, and VDD is a DC voltage that converts to ground in the small signal model. I think we mentioned that last time. Also, VB is a DC voltage that converts to ground in the, so this is the gate of transistor 2, and this is V2 between the gate and source of M2. Here just the names on this one, because they didn't draw the entire model, that's why they call it V1. It should be V2, just to make sure we're not confusing with this one. Okay, so now I'm supposed to find the gain, which is V out over Vn. Now what I want to tell you is that if you look at this current source, what is the value of this current source? It's GMV2, but what is V2? You can see that the gate here, this side of V2 is grounded, and the other side of V2 is also grounded. Both gate and source, they are grounded of this transistor in the small signal model, which makes that V2 equals to 0, and therefore this current source is not existent. Is this part clear? Okay, so the gate and the source of transistor, the upper transistor M2, they are both grounded in the small signal model. And this makes the V2 value equals to 0. So, and the current source G and V2 depends on it. Therefore, it's a 0. Okay. Now, if we look from the out point of view, we see that from this node to ground, there is an R2 and there is an R out 1. So they appear, if you draw it like this, R out 2, and there is R out 1, and there is here GM 1, V1, and here Vn. And this is the gate of transistor 1, this is the source, and here the drain, and here V out. Does it make sense to you that the upper circuit, this model that we draw before and the model down, they are the same? Both from the drain, I see R out, down, 1 down to ground, R out 2 down to ground. So they are in parallel with each other. Okay, and therefore, as you remember from before, as we did that here, V1 equals to Vn. And just give me 1 second, Obed, 1 minute. V out equal GM1 times Vn, and times R out 1 in parallel with the R out 2. And therefore, V out over Vn, yeah, with the negative sign, because the direction of the current is different, minus GM1 times R out 1 in parallel with R out 2. Yes, Obed, please go ahead.
Ma'am, why did you remove GM2V1?
Why I removed this part here?
Yes, ma'am.
Yeah, because this current source, which was here, is equal to GM2 time multiplied with V2. But V2 is 0. Therefore, the entire current source value becomes 0.
All right, ma'am. Thank you.
You got it? Are you sure? It's clear?
Yes, ma'am.
Okay. So now we get the gain, which equals to basically V out over Vn minus GM1 times R out 1 in parallel with the R out 2. Now, if you remember the previous gain, which we did when it was a resistor, it was V out over Vn equal minus GM1 times R out 1 in parallel with the RD. Now, the only thing, this we did it last class. The only thing that has changed here is that RD is being replaced with R out 2. You can see the gain, otherwise the ratio, relation, sorry, they are the same. Only RD is being replaced with R out. And as you said, we said when we look from up here, since we are seeing it from the drain side, it will be an R out 2 up. And therefore, the entire load for us has a value of R out. It's like we have a resistor that has a value of R out. Yes, Ibrahim.
Ma'am, could you move the mic closer? When you start writing, your audio gets very muffled.
Yes, I'll try my best. I'll try to increase my voice. Okay. And this is what we just did here. So basically, this is to solve the problem of headroom that we discussed earlier. We use an active current source as a load. The advantages, basically, because current source has a high output impedance and can take a small voltage drop across it. So these are among the advantages that we get from replacing the resistor with a transistor that acts as a current source. And this what we basically did. If we want to find also the output impedance of the amplifier, the same way we can use just the small signal model, or if you quickly you are looking from the V outside here, in order to find the output impedance, you look what is the impedance up, it's in parallel with the impedance that is down. Okay, so when I look up, I find R out 2, that is going to be in parallel with the impedance down, which is, I'm looking now in the drain of M1, so I will find an R out 1. Therefore, it will be R out 1 in parallel with the R out 2. So this is a quick way of finding it. Obviously, you can go back to the small signal model. And we said when you want to find the output impedance, you need to do two things, if you remember. The first thing, you need to short the input. And second thing, you need to apply a voltage source from the output side that is a test source. We call it Vx, having a current of Ix, and then you will have your output impedance equals to Vx divided by Rx. Okay, now here in this question, it's still a common source. Why? The input you can see is coming here. So the V input is coming at the gate of M2, and we are taking the output from the drain of M2. Therefore, it still remains as a common source because the input is the gate of transistor. The output is taken from the drain of the same transistor. Therefore, it remains as a a common source. Okay, so now the gain of a common source is minus GM of the same transistor where the input is applied. So since it's applied at the gate of M2, we have minus GM2 multiplied with the R out 2, the impedance of the same transistor in parallel with the load. What does my load have impedance if I look down on M1? So now M1 is acting as my load. Though it's, I mean, the circuit is opposite direction now, but you will know that what is the other side is basically your load. So if I look at M1, from which side of M1 am I looking? Am I looking from the drain side? Am I looking from the source side? Or am I looking from the gate side? If I am looking from the drain side, then I will find an impedance of R1. If I was looking from the source side, then I will find 1 over GM1. If I am looking from the gate side, then I will see infinity. Does this make sense? Okay, therefore, since we are looking from the drain side, we are going to see an impedance of R out 1. Therefore, my gain will be minus GM2 multiplied with the R out 2 in parallel with the R out 1. It's similar to what we just did here, except that now the transistor was applied on M1. So the gain was minus GM1 and multiplied with the impedance R out 1, which is down, multiply in parallel with the impedance that you see from up, which was R out 2. So they are the similar thing. You just need to make sure where is your input is applied, where your output is taken from, and what do you see on that load side. Okay. Yes, we did correct. Now I want you little for a few seconds to think about this one. Again, you can draw the small signal model and do all that part, but let's try if we can become a little bit good on this. We just remember that gain equal minus GM, which one, GM1 or 2? Where is the input is applied on transistor M1, therefore it will be GM1. And with the impedance of the same transistor at the drain side, which is here, R out 1, because the output is taken from the drain side. This is an R out. Okay. And in parallel with the impedance that you see at your load. Your load is basically from the V out up looking at our load that's here. Now, if you remember, this was a diode connected, and we are also looking from the source side. So what impedance are we going to see? Do we see an R out alone or what? We will see an 1 over GM2 in parallel with R out. If we just try this as 1 over GM2, I'm okay. So it will be minus GM1 in parallel with the R out 1 in parallel with the 1 over GM2. Is this a good idea if you want to have a large gain? No, it's not, because this impedance will also eventually become almost 1 over GM2. So you will have an entire gain that's minus GM1 over GM2, almost, which is small. Any question? All okay? Okay. And if you open, this is what we just did. If you open the relation of GM1 and GM2, we will end up with canceling things with each other. And when they will be remain again, that's depending on the size of these transistors. Okay. Now I want, if somebody of you try, if you can get this gain. I don't want to force on anyone. I'm just saying if somebody wants to volunteer and say something, which is going to be very highly appreciated. No one. Don't be scared. We are here to learn. Even if we make any mistake, it's okay, as long as we are learning. Okay, I'll just go slowly through it, and if I'll just give you 30 seconds to try yourself to write it down, and just don't tell me even what is the answer. Just take a few seconds to write it down yourself, and then I'll do it to see if you are getting, and if you are not getting, and you want to tell me what issue you or mistake was it there, so I can guide you not to make this mistake again. Okay, I'll wait a few more seconds and then we'll do it. Okay. So we have again, the gain is minus GM with GM1 or GM2. I look with the input is applied where? The input is applied at transistor gate of transistor M2, therefore it will be minus GM2. Now with the impedance of my M2, so it will be R out 2 looking up, and now in parallel with the impedance that I'm going to be seeing down. Which one down? Now, for M1, am I looking from the source side? Am I looking from the drain side or the gate side? This is the arrow is typically your source side. Since we are looking from the source side, we will see a small impedance that is given by 1 over GM 1 here. You can again write in parallel with the R out 1, or you just write 1 over GM 1, both are fine. Any question on this? It's really hard for me in this online learning. If you don't speak up, I cannot assume anything. In the normal class, I see your faces. I know that. Are you getting or not? Here, I have to be like I am talking to myself. I cannot know if you are understanding or not without you telling me. All okay? I hope so. Let's see. So this is what we did. Minus GM2 in parallel with the 1 over GM, in parallel with the R out 1, in parallel with R out 2. Okay, now this we are done now from the common source. I just saw a question from someone. Yes, 1 over GM is much smaller than R out. Yes, this is a correct thing. Yes. And now, yeah, we are done from a common source alone. And that was the easiest one. Now, the common source with degeneration. Degeneration means that your source is not anymore connected to ground. There is a resistor down there between the source and the ground. There is a resistor called RS. In this case, we call it common source with degeneration. We are still applying the input at the gate and taking the output from the drain, but the source is not grounded anymore. There is a resistor down there. And that resistor is going to do some changes in our gain values and in our output impedance that we are applying, that we are getting at the output. So the gain will change and the output impedance will change. Let's see how they will change. How we will figure out what the new gain and what is the new output impedance by doing the small signal model and deriving it from there. Okay, so the small signal model is given here. So I have the Vn is applied at the gate. The source is having RS down to ground, and this is the drain side of the transistor, and we can have RD. Now, in the simplest case, we are doing RD, but you still can replace any load with this RD using a transistor, either from the drain side of that transistor or from the source side of that transistor. Then we will replace this value of RD with that impedance that we are seeing on that transistor. Okay? But for the easiest case, let's assume it's just an RD here. So now we need to remember to find out how the things, yeah, here you can assume also that lambda equals to 0. That's why we are ignoring the R out that should be appearing in the small signal model, just for the sake of simplicity. Okay, so our Vn equals to V1 plus the voltage drop across RS. So what is this voltage drop across RS? With the current that is going through RS. What it is Gm times V1. Why is this? Gm 1 times RS. Why? Because this is an open circuit here. This is an open circuit side. So all this current has continue flowing down. Therefore, all this V and V1 is going into RS. So Vn equals to V1 plus this voltage drop across RS. And if I want to make V1 on one side, so it will be V1 equals to Vn therefore V1 equal Vn divided by 1 plus Gm times Rs. Okay, this is important relation here for us. And now I want to write V out. V out is equal to what? Again, minus Vm times, minus Gm V1 times Rd. Why? Also this current is going through Rd, the same current. So now V out equals to Gm multiplied with Rd, and I want to replace this V1 with the relation that we did here. So it will be Vn divided by 1 plus Gm Rs. So V out over Vn equals to Gm Rd over 1 plus Gm Rs with a negative sign. Still, it's an inverting topology. Okay, so if it was a common source alone, the gain was minus GMRD. Now with degeneration, the gain reduces and it becomes minus GMRD divided by 1 plus GM times RS. So the gain has reduced in case of using this common source with degeneration. Is this clear, derivation? Any question? Okay. Yes, this is the same. Yeah, so here this is the way that they write the gain, but if you multiply up with GM and down also with GM, you will still get minus GM RD over 1 plus GM times RS. So this is the same thing. Okay. Now, if we want to find the gain of this common source with degeneration, now you can see that not my load RD is still the same, but my source resistor RS has been replaced with this transistor, which is named M2. Now, if you can see, this is equal to having a resistor down here because I am looking from the source side of M2. So I see an impedance of 1 over GM2. So these are both are equal to each other. Therefore, writing again, the original was minus Gm Rd divided by 1 plus Gm Rs. So now only my Rs has been changed to 1 over Gm2, the value of it. So minus Gm1 because the input applied at transistor M1, 1 plus Gm1 multiplied with 1 over Gm2. Why? Because Rs value here is equal to 1 over Gm2. Why 1 over Gm2? Because I am seeing M2 from the source of M1, I am looking at the source of M2. And therefore, since I'm looking on the source side, I see 1 over Gm2. If it was connected like this is connected here, and there's a VB here, then then this RS will be equal to R out of transistor. It will be R out. Okay, because I will be looking from the drain side of M2. Is this clear? Any question on it? No question. Okay. So this is the same thing that we just did here. Now, if I have a gate impedance, RG, it will not change anything on my gain and input or output impedance because there is no current that is flowing in this, no current I equals to 0 here on the gate, and therefore it does not affect anything. Okay, just keep this in mind. Okay, now if I want to find the output impedance in the case when I have a common source with degeneration. Remember, if there was no degeneration, the output impedance looking from the drain side will be just an R out. But now, since there is an RS, things has going to change. So again, I revise the two things that you need to do in order to find the output impedance is that you will short the input, this is number one, and you will apply a short at the output having a value of Vx and coming out equals Ix. And your output impedance will be Vx divided by Ix. Okay, those are the steps that we will follow to find the output impedance. The first is that V1 again equals to what? It's equal to the opposite voltage that is applied on RS. So V1 equals to minus RS multiplied with IS. Let me explain this clearly again. You know that all this current that is coming from the test source Ix coming here will divide into two branches that they will again meet and come here. Nothing will go on this side. All will continue down into Ix. And this will also have a value of Ix. Now from this node till ground, that is in this direction, the voltage here is Ix multiplied with Rs. But V1, it has an opposite polarity. The negative sign is here and the positive sign is up. Therefore, V1 is opposite of the polarity across the RS, which is RS multiplied with Ix. That's why this negative sign came from. That is here. Okay. Now, where I were? Yes. So what do we want to do now? We still want to find a relation between Vx and Ix. So first we wrote a V1 equal minus Rs times Ix. Now I want to see those two currents that they are going to basically, what is the value of Vx? Vx is the voltage drop across this R out plus the voltage drop across Rs. What is the voltage drop across R out? It will be R out with the current flowing through it, which is Ix minus Gm times V1. What is V1? It's Rs multiplied with Ix. Therefore, with a negative sign, so this is going to become positive. Plus Ix multiplied with Rs. Where this came from? We want Vx will equal to the voltage drop across R out plus the voltage drop across Rs. What is the current going through R out? It's Ix minus this portion that goes to Gm V1. So it will be Ix minus Gm times V1. What is V1? It is minus Rx times Ix plus the voltage drop across Rs, which is Ix times Rx. I know it's too many things, but this is how we should deal with it. Okay, so now I'll try to simplify and we make Ix outside so we can divide with it. So Vx will become, let's do it slowly. R out times Gm times Rs times Ix plus Ix times Rs. Let's take Ix outside, so it will be R out plus Gm R out Rs plus Rs. This is Vx, so Vx over Ix, which is equal to R out of this amplifier will equal to R out plus Gm R out Rs plus RS. So this is the output impedance of the amplifier. So instead it was just an R out alone. Now it will be increased by this portion when we do a common source with degeneration, when we degenerate the source. So the gain has reduced, but the output impedance got increased. Any question on this? All okay? Okay, so these are the steps that we have. Yes, so basically they round it and remove this RS part here, because typically RS is a small value. So you reduce this part here, this RS, and it will be just left with an R out plus GM R out RS. Okay. Now here, if we want to find the impedance of this that we are seeing here, the only thing it R out is basically, if you remember, we just did the relation R out of the transistor, R out 1, and plus GM R out 1 times RS. Now here in this example, the RS has been changed and replaced with this transistor M2. Now, since we are seeing M2 from this side, it's a diode connected. Why diode connected? Because the gate and the drain, they are shorted with each other. Since they are diode connected and we are looking down there, then we will see an impedance that equals to 1 over GM2 in parallel with the R out 2. Even if you again said 1 over GM2, it will be still correct. So the gain going to be, you know that it was plus RS, but you can ignore this part if you want. So it will be R out 1 plus GM1 R out 2 times RS. What is RS here? 1 over GM2 in parallel with the R out 2. Okay. Any question on this? No question. Okay. Now they just here the R out. They took it outside. I mean, those two terms, they took R out as a common, and they added the RS. Then we will be left with 1 plus GM1 multiplied with 1 over GM2. Sorry, this should be GM R out 1 in parallel with the R out 2 plus 1 over GM2 in parallel with the R out 2. So those are the same things. Here they ignored the R in parallel with the R out 2. They just consider it 1 over GM2. Yeah, as it's mentioned here. Any question? Okay, what about this one? Can anyone guess? So only the part that GM, sorry, the RS is going to be replaced with R out 1 plus GM1, R out 1, R out 2 plus R out 2. This is the original RS. It has been, since we are looking in the drain of M2, it will be an R out 2.
Ma'am, it's R out, not AV.
Yes, thank you. Yes. Thank you. I'm happy that you are focusing with me. Thank you. Okay, any question? Yes, so this make sure that this is an R out. Okay. Yes, now we just want to talk about slightly about the biasing of the amplifier. So sometimes when you apply the input, basically we can bias our common source using this way. So we have a sort of a voltage divider here to provide a Vx voltage that's sufficient to make this transistor in the saturation region. And whatever the V input is basically going to have any DC voltage different from the Vx, we separate them or we prevent this DC input DC voltage to come to the amplifier using this capacitor, which is going to act like it's an open circuit for any DC voltage, and it will only the AC component of this voltage to the amplifier. So the Vx here will be given by R2 over R1 plus R2 times VDD. It's like a voltage divider. Okay. And we have an RS here that we can basically have it to stabilize the point or the biasing point of the amplifier. If it was just a ground, the amplifier can change their or like not have a stable biasing point, but with the having a resistor, we can control what exact value of RS, of the voltage drop across it. And we will discuss this in more details later when it's we come through it again. But you can also see here, if you doing this approach will change the input impedance of this amplifier. So it's not infinity anymore. It will be R1 in parallel with the R2. This is the Rn. Because here it's an open circuit, but at this point we are seeing in the small signal model R1 to ground, because VDD will be replaced with the ground, and down R2 to ground. So they are appearing in parallel with each other. Okay, and I think this we can discuss it later. The point of this biasing resistor, or sorry, bypass resistor, capacitor, what happened? This basically at the DC, when we want to set the DC operating point of the amplifier, it will be act as an open. So it's like it's not there, and then we have a common source with degeneration and we bias it. Once we go at the higher frequencies, it will become a short. Therefore, this it's a short to ground in parallel with this RS. So this RS will like disappear because it's in parallel with the ground. So it is like it's not there. And therefore the gain will improve because the circuit will not become a common source with degeneration again. It will become just a common source. I think that this part I will elaborate on it later, so don't worry too much if you didn't get it now. Okay, I think I'll go through this later. Any question on the common source with degeneration or a common source or whatever, something we did so far?
Ma'am, what does RS do in biasing?
It's basically, they say it's fix the voltage of, meaning that, let me go here back again. Now, if this Vx move up and this Vd move up, if the since VDS remains VD minus VS and VGS remains VG minus VS, they will stabilize each other, meaning that if this VG goes up, the VGS will go up. Okay. And now,
Okay, okay.
Yeah, I can just elaborate it a little more. If you still don't get it, it's okay. I just want to say this, I explain it to you. So if VGS goes up, the current here, ID, will go up. Yes, because ID depends on the VGS. And once ID goes up, the voltage Vs here is Rs times ID. Yes. So therefore, this voltage drop across Rs will also increase because the I has increased, the current increased. Since Vs is going to increase, therefore this will reduce VGS again. So it's like kind of a mechanism to fix the any changes in the VGS. VG increase, current VGS will increase, current will increase, VS will increase, VGS will reduce. So we are solving this issue, making sure that we remain VGS in a controlled manner. Anybody got this?
Yes, ma'am.
Okay, thank you. If a VS was just connected to ground, then we can, I mean, when ID increase, there is nothing that we can do about it. But since there is a resistor down, the VS will also be changed. If it was just connected to ground, it will remain ground. But the voltage drop across RS is related to the current. So we have to stabilize the biasing point easier than in just if VS is connected directly to ground. I'll go through this once more again when we come to it in other chapter. I think it appears again. I'll revise it in a more clear way, inshallah. Okay, now we'll move to another type of amplifier, which is called a common gate amplifier. In this amplifier, how to identify it? Your input is going to be applied to the source side of the transistor, and we are taking the output from the drain. And our gate will be connected to DC voltage. Again, so our input is applied at the source side. We're taking the output from the drain. Okay, and our gate is connected to a DC voltage biased to a certain voltage. Okay, now I want to draw for you the small signal model so we figure out how it came. Okay, so we have an RD here. Again, we replace the VDD with the ground in the small signal model. This is the drain. And here we need to assume, for simplicity, lambda equals to 0. So there is no R out. And here Vm times V1. And this is the source. And our input is coming here. And this is the gate is grounded. Why? Because it's connected to a DC voltage that is going to be replaced in the small signal model with the ground. And this is V1. No, yes. Okay. So this is the small signal model. Now, how V1 is related to Vn? V1 is equal to minus Vn. Can you see this? Because this is a negative sign from the source, and this is at the gate is a positive direction. And this is the opposite polarity of the Vn if we make a KVL in this loop here. So it will be V1 and plus Vn equals to 0, and therefore V1 equals to minus Vn. Now Vout is equal to minus Rd because the direction is opposite, multiplied with a Dm times V1. So I replace V1 with the Vn, so it will be Dm times Vn times Rd. The negative sign will go away, and therefore Vout over Vn will equal to Dm times Rd. Okay, and this is our voltage gain. So you can see that the gain is equal in terms of a value to the common source amplifier, but that was an inverting with the negative sign. This is non-inverting, it gives us a positive gain. Okay, this is the only difference, that this gives a positive gain, it's a non-inverting, and the other is an inverting topology. Any question? Okay. We just need to remember that or know that also this topology suffers from the voltage headroom problem, where basically in order again to get the large gain, we need to to get or to have a larger RD. And if we have a larger RD, we are at the risk that this voltage will drop, because a larger voltage drop will be seen as the RD, and this makes our transistor might leave the saturation region. So in order to maintain M1 in saturation, the signal or the V out should not fall below this V bias minus V threshold. Okay, because we need to make sure that VDD minus RD times ID, which is the V, this is equal to V out. This minus Vs, or the Vn here, Vs equal to Vn. This should be greater than Vb minus Vs. Vs can be cancelled with a Vs, and therefore a Vb sorry, yes, minus V threshold here. Okay, so Vb minus V threshold should be always less than V out. So we should not fall below this value. So equal means. Okay. Let's take last thing is this example. So we have a microphone that has a DC level of 0, and it derives a common gate stage biased at ID equal half milliamp. I have VM coming here, and this is a VB, and this is RD, and this is the out taking from here, and this is VDD. Okay, now so ID equals to half milliamp, W over L equals to 50. We have mu and COX 100 microamp per volt square. Threshold voltage is 0.5. VDD is 1.8 volt. So we need to decide the maximum allowable value of RD and the maximum voltage gain then that we can get from this value. And we need to ignore the channel length modulation. Mostly in the case of common gate, we will always be given to ignore the channel length modulation for the simplicity of calculations. Okay, so the first thing is that we need to, from the value of ID, what can we get? ID equals half mu n COX W over L VGS minus V threshold square. So we know ID, half milliamp. We know mu and COX 100 micro. We know W over L 50. We don't know VGS, and we know V threshold is half. So everything known except the VGS. So from here we get the VGS. Basically, if you do the calculation, it will be equal to 0.947. Just this also example from the book. Volt. Okay. Now again, we need to make sure that VDD minus RD times RD minus Vn, which is Vs here, greater than Vb minus Vn. So this will go with this one, minus V threshold. One will go with this one here. And VDD is 1.8 minus ID is 0.5. Yes, times RD. Now, what is the value of VB? VB is equal to VGS. Why? Because VS equals to 0. How did I know this thing? Because of this sentence here. DC level input have, because input is coming from microphone, has DC level of 0. Therefore, we are considering the input at 0 DC level. Therefore, this Vs is equal to 0. Why can't you see that screen? This part down is not shown. So Vs equals to 0. And therefore, Vb equals to this 0.97447 minus V threshold is 0.5. Now, from this calculation, we find that RD, if we take the things and arrange them, should be less than 2.71 kilo ohm. So this is the largest value that RD can take. If you take any value larger than this, you will leave the saturation region. Okay, now what's the gain at this value? We know that the gain of a common gate is a GM RD. Now we need to calculate the GM. GM is basically given by, if you remember, square root of 2 mu n COX W over L times ID. So we know all of these values here, and times RD, which we just found the 2.71 kilo ohm. This is the largest value, and this gives me a largest gain of 6.06. I don't have space to write down, you cannot see it. So this is the largest gain that we can get. So the gain will be less than this value. Any question on this example? It's clear? Okay, also here summarized for you. Any question, please? We're done here. Don't want to cover, I mean, the other parts remaining will cover next lecture. But if you have any question or you have any comment or any suggestion, please tell me. All okay?
Are we going to study the degeneration stage of this common gate, or does it have one?
Yes, we will, there is a part, we will cover it the next time when there we'll talk about how to find input output impedance, and basically if there is a source impedance, means if there is any resistor here, RS, how it's going to affect the gain. It will be similar to the common source with degeneration. Yes, there is this part, but we will talk about it later. I mean, next time, inshallah. Any other question? Everything we talked about clear? Please do revise it before the next lecture so we make sure that you are not missing anything, because we will again build on these things.
Ma'am, how did you write the voltage equation? VDD minus ID RD minus V in should be greater than.
Yeah, how I did this, a good question. So basically, this part is VDF, all this. So it is the VDD minus the voltage drop across RD, this part here. So this is initially, this is just VD. And the VS is basically no resistor at this moment here. VS is equal to VN. So I have space here, let me repeat it. So this is Vn and it's equal to Vs, and this is Rd and this is VDD. So Vd is equal to VDD, this is VD, minus Rd times Id, and Vs equals to Vn, and Vgs equals to Vb minus Vs. So therefore, we need to make sure that VDD, this part is VDD, VD minus Vs. This is just VD, and should be greater than VB minus Vs minus V threshold. In this equation, here they cancelled already Vs with the Vs. Therefore, it remains VD greater than VB minus V threshold. Does this make it clear or still confusing?
Yes, ma'am, it does.
Okay, thank you.
It's clear.
So we
It's
will
clear.
meet inshallah on Wednesday. And if you have any question or anything, please do email me so we can, or next class in the beginning, we can answer it. Thank you.